Hello everyone, today we are presenting our project based on the article Do's and Don't of Machine Learning in Computer Security by YASSINE Security Symposium. The content of our presentation: first, introduction and machine learning for computer security and common pitfalls of machine learning in computer security and the prevalence analysis, and finally conclusion and future work. The revolution of machine learning extends to diverse fields, particularly in computer security, where it solves many problems. But, however, it's not without its challenges. Heavy reliance on statistical properties in machine learning workflow might introduce bias and inaccuracies, compromising the reliability of scientific research. The second section, machine learning for computer security. Machine learning aims to create automated decision-making machines through a training phase. This involves using a given machine learning algorithm to analyze existing data, resulting in the development of a machine learning model. The model representing learning knowledge is then assessed for performance using validation data before deployment. So here is an exemplary workflow of the training and validation phases is schematically duplicated in the figure below. So the first phase, machine learning training, so the model trained from data, and the second phase is machine learning validation. So here the model can make decision if this, for example, this file if benign or malicious. There is many types of machine learning, and here is a typical machine learning algorithms. We can deviate it for supervised and unsupervised, and shallow and deep. So supervised can be deep and shallow. An algorithm can be deep if it relies on neural network. Otherwise, it's shallow. Algorithms requiring labeled data are used for supervised tasks. Otherwise, they can be used also in unsupervised tasks. So in unsupervised tasks can be deep if we use deep Boltzmann machines, stacked autoencoder, generative adversarial network, and shallow. We use clustering algorithms, association rules, reinforcement learning. For the supervised can be deep, so we use convolution neural network and feed-forward neural network and recurrent neural network, and can be shallow if we use random forest and logistic regression and K-Rieck neighbor and decision tree. Machine learning instantly become a powerful weapon in the fight against cyber threats, tackling a variety of challenging problems in computer security. And here is some key areas: malware detection and prevention, and vulnerability discovery, and network intrusion detection, and phishing attack detection. For the malware detection and prevention, machine learning can analyze apps' behavior patterns to detect suspicious activities that deviate from normal usage and tracks app resource usage, CPU, memory, network. And vulnerability discovery, using machine learning to scan code bases for common vulnerabilities such as buffer overflow, SQL injection points, and across-site scripting, and flaws, and monitors program execution to identify vulnerabilities that may not be apparent in statistic analysis. And network intrusion detection, using anomaly detection to learn normal network traffic patterns and flags deviation that may indicate intrusion attempt, such unusual traffic volumes, new port scans, or unauthorized access attempt. For the phishing attack detection, analyze email content and website feature to identify subtle plots that may indicate a phishing attempt. And I give the word to my colleague FOUAD for the third section.
Hello. Next section, common pitfalls of machine learning and computer security. The focus is on 10 common pitfalls, and there are recommendations on how to mitigate them. Here is machine learning workflow. Pitfalls 1. Sampling bias, and pitfalls 2. Label inaccuracy in data collection and labeling. Data snooping and spurious correlation and biased parameters in system design and learning, and inappropriate baseline and inappropriate measures and base rate fallacy in performance evaluation and lab-only evaluation, and inappropriate threat model pitfalls in deployment and operation. These pitfalls are grouped with respect to the stages of a typical machine learning workflow. For each issue, the authors provide a brief description, discuss its impact on the security domain, and make recommendations. Furthermore, colored lines depict the proportion of lives experiencing a deadlock, with warmer colors indicating the presence of a deadlock. Data collection and labeling. Pitfalls 1. Sampling bias. The collected data does not sufficiently represent the true data distribution of the underlying security problem. 60% this pitfall is present in 30 papers, and 20% this pitfall is not present in these papers. There are some recommendations. Avoid merging data from incompatible source. Extending the dataset with synthetic data. Pitfalls 2. Label inaccuracy. The ground truth labels required for classification tasks are inaccurate, unstable, or erroneous. 57% this pitfall is present in these papers. 13% this pitfall is partly present in these papers. There are some recommendations. Using robust models or loss functions. Actively modeling label noise in the learning process. Cleansing noise label in the training data. In system design and learning, pitfalls 3, data snooping. Artifacts unrelated to the security problem create shortcut patterns for sparching class. 57% this pitfall is present in these papers, and 13% this pitfall is not present in these papers. There's some recommendation. This data should be split early during data collection and stored separately until the final evaluation. Temporal dependency within the data should be considered when creating the dataset splits. Pitfalls 4. Spurious correlation. Artifacts unrelated to the security problem create shortcut patterns for separating classes. 20% this pitfall is present in these papers, and 70% this pitfall is not present in this paper. There are some recommendations. Recognizing the contextual variability of correlation in machine learning. Ensuring that learned correlations align with the intended goal of the learning-based system. Next pitfall. Biased parameter selection. The final parameters of a learning-based method are not entirely fixed at training time. 53% this pitfall is unclear text in this paper, and 10% this pitfall is present in these papers, and 30% this pitfall is not present. There are some recommendations. Strict data isolation is already sufficient to rule out problems when determining upper parameters and thresholds. Next pitfall. Inappropriate baseline. The evaluation is conducted without or with limited baseline method. 20% this pitfall is present in these papers, and 70% this pitfall is not present in these papers. There are some recommendations. Inclusion of sample models in the evaluation process. Sample models are characterized by ease of explanation, lesser computational dominance associated with simple models. Next pitfall. Inappropriate performance measures. The chosen performance measures do not account for the constraint of the application scenario. 33% this pitfall is present in these papers. There are some recommendations. Performance measures in machine learning are application specific. Lack of general guideline for choosing appropriate measures. Next pitfall. Buzz rate fallacy. A large class imbalance is ignored when interpreting the performance measures, leading to an overestimation of performance. 10% this pitfall is present in 30 papers, and 20% this pitfall is partly present, and 53% this pitfall is not present. There are some recommendations. Security challenge often entail the detection of rare events like threats and attacks. Metrics accounting for class imbalance, such as persistence and recall, are generally effective performance indicators in these cases. Deployment and operation. Lab-only evaluation pitfall. A learning-based system is thoroughly evaluated in a laboratory setting without discussing its practical limitation. 47% this pitfall is present, and 37% this pitfall is not present, and there are some recommendations. Critical consideration of temporal and spatial relation in the data, addressing typical dynamics encountered in real-world scenario. Next pitfall. Inappropriate threat model. The security of machine learning is not considered exposing the system to a variety of attacks, such as poisoning and evasion attacks. 17% this pitfall is present in the papers, and 37% this pitfall is partly present, and 13% this pitfall is not present. There are some recommendations. Essential need for a precise definition of threat models. Alignment of system evaluation with defined threat models. Necessity to assume an adaptive adversary in many cases. Next section, prevalence analysis. For the prevalence study, the authors adapt three processes. First process is paper selection. The authors selected 30 papers from top conferences to independently scrutinize and dissect how the presented pitfalls manifest within the selected papers. And second process is review process. For amateur calls, review process, the assigning to independent reviewers with expertise in machine learning and security to assess papers for pitfalls. Pitfall can be present but discussed, can be partly present but discussed, can be not present, and can be unclear from text. Next process, authors' feedback. To promote community engagement, the reached out to 135 authors of selected papers, conducting an anonymized survey to collect feedback on three findings. The emphasis was on safeguarding authors' privacy and fostering an open discussion. So how does it look like? So the most prevalent pitfalls are sampling bias and data snooping, which are at least partly present 90 and 73 of the papers respectively. Also they identify an appropriate performance measures lab only evaluation at an appropriate threat model to be at least partly present in more than half of the papers. All pitfalls are present in at least some of the review publication, and interestingly, only in 22% of these cases are the pitfalls discussed. So, what can we infer from? Pitfalls are prevalent even in top research. This result, in summary, they see here that many of these pitfalls commonly occur even in very carefully conducted top research. To continue, I'll hand it over to my colleague Abdellah.
So the impact analysis. They say that these pitfalls are coming. It doesn't really show how serious their impact is, and it's of course difficult to quantify this. So they are hoping by systemizing them in this way we can start to raise awareness and reduce their prevalence and future research. So they looked at the handful of representative case studies where they examined the impact of different pitfalls in these settings. So in particularly they looked here at this case study. Android malware detection, and there is 3 pitfalls: sampling bias and spurious correlation, inappropriate performance measure, and the authorship attribution. There is 2 pitfalls: sampling bias and spurious correlation. In vulnerability discovery, we have 3 pitfalls: label accuracy and spurious correlations, and inappropriate baseline. In the network intrusion detection, we have 2 pitfalls: inappropriate baseline, lab only evaluation. So, for the Android malware detection, a common source of recent mobile data is the Android project, which collected Android apps from a large variety of sources, including the official Google Play Store and several China's market. So here is a number of APK's apps in each market. So some analysis of Android datasets. The share of malware in datasets applications are flagged by at least one antivirus product. So we say that Google Play, we have 22% of malware and 78% is a good war. In the app China we have 50 malware and 50 good war. In the share of malware in datasets applications are flagged by at least 10 antivirus products. We see in Google Play we have only 1% of malware and 99% is a good war. If we see App China, there is 17% is a malware and 83 is a good war. So researchers encounter challenges in predicting apps malignancy due to the sampling bias arising from merging data from diverse sources, even affecting widely used dataset like the Android Zoo dataset. For the impact study in mobile malware detection, the plots illustrate the probability of obtaining an app from a specific store regardless of antivirus detection, revealing a potential spurious correlation, whereas malicious app detected by at least 10 scanners are more likely from Chinese market, and benign apps are predominantly from Google Play. Notably, a similar sampling bias was observed in the Dragon dataset. So in the plot we see that Google Play, if we augment the antivirus detection, we see the correlation, the negative correlation between the number of antivirus detection and sampling probability. and a positive correlation between sampling probability and number of antivirus detections. So the experiment examined the impact of Android app origins, Debian and OPSEC on classifier performance using two datasets on merging benign and malicious apps from diverse sources and another with malware exclusively from Google Play. So for the results, the experiment results show how sampling bias affect results. The pitfall 1. The URL playgoogle.com is among top feature in the dataset 1. Using accuracy would have underestimated the process of bias, the pitfall 7. So for the conclusion and the future work, I give the word to my colleague FOUAD.
Finally, conclusion and future work. The study identified 10 several pitfalls impacting performance and research validity, ranging from database to overfitting. What presented actionable recommendations are provided to help researchers avoid these pitfalls, fostering sound design, development, and evaluation of machine learning security systems. Future work. The evolving landscape of both computer security and machine learning necessitates continuous monitoring of trends and threats, updating the do's and don't as new vulnerabilities and attack techniques emerge. Collaboration between security and machine learning researchers, fostering cross-disciplinary collaboration to address the unique challenge of applying machine learning to security domain. Open source tools and datasets, encouraging the development and sharing of open source resources to accelerate research and development in the field.